This is Euclid Book 1, proposition number 37, and I can tell you right now, this thing is a bear to draw. I cannot tell you by how much. First of all, you're going to start with a simple triangle, A, B, C. And that's about the simplest thing in this whole proof. Okay? Now, you're also going to end up drawing a triangle called DBC. Now, ABC and DBC are going to be drawn on the same base. This will be the base of both the triangles. And eventually we're going to show you, we're going to actually connect A to D together, and then we're going to say that AD is parallel to BC, so these two triangles are connected to a parallel line to BC. And that is all given to you. What Euclid wants you to do is to prove that the area inside DBC is equal to the area inside ABC. Now, I will grant you right now that this is kind of a crude drawing. You're going to start saying, well, this doesn't look exactly right, whatever. That's true. I have substandard equipment, that's why. But I assure you, if you drew this with proper equipment, things would look exactly right, and this would actually work. Alright, so, forgive the inaccuracies, we're going to do as best as we can. First of all, how in the heck do you draw the line EADF? That's a good question. You're going to go back to proposition number 23. Euclid Book 1, proposition number 23. And what you're going to do is you're going to duplicate this line here, way up here, and then you're going to duplicate this line here, way down here. And when you do, wherever they cross, that's going to be parallel. This whole line here will end up being parallel to this line right down here. Alright. Now comes the real tricky part. Using Euclid Book 1, proposition number 31, boy, there's another trip. Euclid wants you to draw a line from point B to point E, and he wants this line parallel to AC. And then he wants you to draw a point from point C to point F, and he wants it parallel to BD. Now, how are you going to do this? Well, you're going to use Euclid Book 1, proposition number 23 all over again. Alright? And so what you're going to do is you're going to duplicate AB and AC right down here. These two lines right here will represent AB and AC, and when you cross them together, they're going to meet at a certain point. It's going to be right down here, and then, well, actually not right there. It's actually going to meet right down here. Okay, when it does, you're going to draw this line from here all the way up to here, and you're going to get BE. Alright? Same type of deal over here. You're going to duplicate this line and this line here and here, and when you do, they're going to meet at a certain point, and you're going to draw that line. It's going to be CF. Alright. Now, according to Book 1, proposition number 35, we said that parallelogram EBCA and parallelogram DBCF are equal in size. Those two parallelograms are equal in size. Now, that doesn't mean that their lengths are all equal, but what it does mean is the area contained by these two parallelograms are exactly the same size. Okay. Now, Euclid goes on to say that triangle ABC is 1/2 of parallelogram EBCA. And it just so happens that AB bisects EBCA. Okay? And so therefore, that means by Book 1, proposition number 34, that triangle ABC has the same amount of area, okay, as EBA. So EBA and ABC have the same amount of area. ABC is 1/2 of EBCA. Okay? Same likewise deal, using again proposition number 134. This is book 1, proposition number 34. We can now say that triangle DBC is 1/2 of the area of parallelogram DBCF. Okay? So DBC is 1/2 the area, DCF is the other half of the area. Now, if you subtract equals from equals, which we in this case we'd be subtracting EBA from EBCA, and we would subtract DCF from DBCF, then whatever's left, these two right here would have exactly the same area. And that's what Euclid was trying to prove. And he got it done. Alright, I will tell you more in a future video, so stay tuned.